to this session on measuring the unemployment gap. So I am Emmanuel Saez, and I will be chairing this session. So we have 4 presentations of 20 minutes each on that issue of measuring the unemployment gap. Then Régis Barnichon will be our general discussant, and he will talk for 20 minutes. And then we'll open it to the audience for 20 minutes of questions and answers. So people in the audience, the attendees or the panelists can use the chat to type in your questions. So I will be monitoring the chat. So during the presentation, I may intervene, if I see in the chats need, for clarifying questions so that we can all understand the presentations the best. And then after all the presentation, I'll select from the chat the best questions, and if it's possible and there is extra time, I open it, for voice from the audience to voice directly your questions. So we are going to start with Pascal Michaya from Brown University telling us about beverage unemployment gap. Pascal, go ahead. You have 20 minutes.
All right. Well, thanks. Hello, everybody. I hope everybody's doing well. So in this paper, Emmanuel and I are trying to figure out whether the labor market operates efficiently or not. And answering this question, of course, has a lot of implications for how we model the labor market and also for policies, labor market policies, and macroeconomic policies. So the statistics that measures how far the labor market is from efficiency, that's the unemployment gap, which we define as the actual unemployment rate minus the efficient unemployment rate. And so our goal is to develop a measure of the unemployment gap and then apply that measure to the US labor market to see what we get. So the approach that we are going to follow in this paper is a sufficient statistic approach from public finance. So that means that first, we are going to express the unemployment gap as a function of sufficient statistics. And so we are looking for statistics that, first of all, apply to a broad set of models so that our unemployment gap doesn't depend on a set of narrow assumptions. And second, we are looking for statistics that are easily estimable, so that our formula for the unemployment gap is easy to implement, in particular for policymakers. And then, so once we have our formula, we are going to apply the formula to the US labor market. So we are going to measure the sufficient statistics in the US labor market, and then we are going to compute the US unemployment gap. So to derive this sufficient statistic formula, what we are going to do is we're going to assume that the labor market features a beverage curve. So what's a beverage curve? So you see it here for the US. It's a negative relationship between the vacancy rate and the unemployment rate. So this is the US labor market for the past 10 years, all the way to the end of 2019. And you see the beverage curve here is this downward sloping relationship. And the reason why we assume a beverage curve is that many labor markets actually feature a beverage curve. So in the US, it has been observed since the 50s, but many other countries also have a beverage curve. And that beverage curve is going to be very important because it's going to constrain what the social planner can do. So it's going to be a key element when we compute our efficient unemployment rate. So the efficient unemployment rate, it's the unemployment rate that a social planner would set. So a social planner who tries to maximize welfare by allocating labor between 3 different things: production of goods and services, recruiting of workers, and unemployment. And so, of course, if you're the social planner in that setup, you want to reduce unemployment as much as you can, because, of course, unemployment is costly from a welfare perspective, because unemployed workers, they do not produce as much as employed workers, even if there is some home production. You also want, if you could, you would also want to reduce the vacancy rate as much as possible, because when you have vacancy posted, it means that you have to allocate labor to recruiting instead of production, and that's going to reduce welfare. So think about the AEA meetings and all the recruiting season that's about to start. You're going to spend a lot of time interviewing candidates, going to job talks. And so all this time is time that's taken away from research and that's devoted to recruiting. So if you could, you would get rid of that altogether. But of course you can't. So that's where the beverage curve kicks in. The social planner has to respect the beverage curve. You cannot, put the labor market away from the beverage curve. So if you're a social planner, what we're trying to do is to allocate labor efficiently between, recruiting, production, and unemployment subject to the beverage curve. So, for instance, just to illustrate how our methodology works, you could ask, is this point that I'm showing you on the beverage curve, is that efficient? So to figure that out, we need to introduce a second curve, which is the ISO welfare curve. So it looks something like this. It's a set of points that all have the same welfare, the green line here. And it's downward sloping because both unemployment and vacancies are costly from a welfare perspective. And all the points that are in the green area inside, these are points that have higher welfare because they have less vacancy and less unemployment at the point on the curve. So now, is the orange point efficient? Well, of course, it's not here because you have points that are on the beverage curve and that are inside this welfare curve, so they have higher welfare. So where is the efficient point here? Well, following standard kind of Econ 101 logic, it's going to be the point of tangency between the ISO welfare curve and the beverage curve. So here, our efficient allocation on the labor market is at the point of tangency here. So mathematically, the efficiency condition is given, by this kind of simple abstract formula. It's the point where the slope of the beverage curve is equal to the slope of the ISO welfare curve. And what's the slope of the ISO welfare curve? Well, the ISO welfare curve is just like a social indifference curve. So in the same way that the marginal rate of substitution is the slope of an indifference curve, the slope of our ISO welfare curve is going to be a social marginal rate of substitution between unemployment and vacancies. And of course, because both unemployment and vacancies, they reduce welfare, the marginal rate of substitution here is the social marginal cost of unemployment divided by the social marginal cost of recruiting. So that's our efficiency condition. The slope of the beverage curve has to be equal to the ratio of the social marginal cost. Now, so that's the logic. Now, the issue is that this is not very easy to implement. So we need to transform this kind of abstract formula a little bit to have a formula that we can actually take to the data. Once we do that, we get this formula here. So this formula gives us the efficient labor market tightness. So the labor market tightness, as in any kind of labor market model, is the number of vacancies per unemployed worker. So, and we call it theta. Graphically, the labor market tightness is the slope of this pink ray that you see. Okay, so this labor market tightness at efficiency, it has to be equal to 1 minus zeta, where zeta is a social value of non-work, divided by epsilon, where epsilon is the elasticity of the beverage curve times kappa, where kappa is the recruiting cost. And so you can see what's in the denominator. Epsilon and kappa, these are two statistics that we'll be able to estimate. So epsilon will do it by estimating, slope of beverage curve. The recruiting cost, we're going to measure it using a large survey that the census conducted among US firms to measure recruiting cost. And then in the 1 minus zeta, so zeta is a social value of non-work. To measure that, we're going to use a reveal preference evidence. So we're going to use two sources of evidence, one from administrative data, one from a large field experiment that will tell us how people value non-work relative to work. And using that, we'll be able to compute the efficient labor market tightness in the US. Once we have the efficient labor market tightness, using also the beverage curve, as you can see, once you have the beverage curve, once you have the slope of the ray, you can figure out what is the efficient unemployment rate. And then once you have the efficient unemployment rate, you just look at the distance between your efficient unemployment rate and the actual unemployment rate, and you get your unemployment gap. Okay. So because this is a short presentation, I can't give you all the details about how we estimate the statistics. All of this is in the paper. But once we compute all these three statistics, we get this result. So this is the key graph of the paper. It's showing you the actual unemployment rate in the US. That's the purple line, and it's giving you our estimate of the efficient unemployment rate. That's the pink line. And of course, the gap between the actual unemployment and efficient unemployment, that's your unemployment gap. So what do we see here? Well, we see that the efficient unemployment rate, it's quite stable over time. You can see we have from the 50s to today, you have an efficient unemployment rate that varies between roughly 3% and 5.6%, but it doesn't move too much. And especially since the 90s, it's especially stable. The average value of the efficient unemployment rate is 4.3%. So a first takeaway from that is, as you can see, most of the time, the unemployment rate in the US is not efficient. The unemployment gap is not zero. So that means that in general, in the US, the labor market does not operate efficiently. Furthermore, what you can see is that the unemployment rate is actually above the efficient unemployment rate. And in fact, the average unemployment gap in the US, according to our estimate, is roughly 1.4 percentage points. So that means that in general, the US labor market is inefficiently slack. So that's a second finding. And then the third key finding is, of course, that the inefficiencies are exacerbated in recession. So you can see the recessions are given by the gray areas. And the unemployment gap really spikes in all recession. And so, for instance, in the Volcker recession in the 1980s, you had an unemployment gap of about 6 percentage points. In the Great Recession, you have an unemployment gap of roughly 6.2 percentage points. So you have really large deviations from efficiency in recessions. So what are the implications of this finding? So you have a range of implications. So first, when we are thinking about designing models of the labor market, these type of findings are going to be important. So for instance, in the matching literature, we always wonder, should we set wages using Nash bargaining, or should we use rigid wages, or should we use competitive search? Well, and these days, a common kind of popular assumption is to have competitive search on the labor market. But with competitive search, your labor market is always efficient. So that seems to be really at odds with the type of evidence that we show here. And in contrast, assuming rigid wages seems to be much more in line with what we get here, because if your wages are rigid, you're going to get a counter-cyclical unemployment gap. So that would be one implication here of the findings. You also have implication for policy. So for instance, monetary policy, if you have a model in which a divine coincidence is true, then monetary policy would want to bring the labor market always at efficiency. And even if the divine coincidence doesn't hold, Blanchard and Galli have showed us that you always would want to try to reduce, even if you don't eliminate, the unemployment gap. And so in all these types of model, here, given that the unemployment gap is especially large in recession, what the central bank would like to do is always reduce interest rates in recession to try to reduce the unemployment gap. So you would have systematically counter-cyclical monetary policy. But it's not only monetary policy. This type of results also apply to fiscal policy. So Emmanuel and I have a paper in which we show that optimal government spending should always try to reduce the unemployment gap if there is an unemployment gap. And so in a world like this, in which the unemployment gap is counter-cyclical, given that an increase in government spending reduces the unemployment rate, what you would want is to have a fiscal policy that's systematically counter-cyclical. So you would want to have more government spending in bad times than you would want to have less government spending in good times. And it's not only macro policies. So we've done some work with Emmanuel and with Camille on unemployment insurance. And here again, optimal unemployment insurance also depends on the unemployment gap. So when you have a counter-cyclical unemployment gap like this, and given what we know about the effect of unemployment insurance on tightness and unemployment, the implication is that we would also want to have a counter-cyclical unemployment insurance over the business cycle. So unemployment insurance that's more generous in bad times and less generous in good times. So all of this comes out of this type of results. So now what I want to show you a little bit is look at what happens if we use different calibration for the statistics. So here I'm showing you our preferred calibration. But of course, there is some uncertainty about the estimate of the beverage elasticity. There is some uncertainty about the estimate of the social value of non-work. So let me show you a bit what you get if you allow for a range of calibration. So this is what happens if you look at the range of efficient unemployment rates that we get if the beverage elasticity is allowed to span its 95 confidence interval. And so what you can see, and so especially at the end of the sample, you can see that actually it doesn't affect our results too much. And in particular, after 2000, when we had better vacancy data because the JOLTS survey was available, you can see that the confidence interval for the beverage elasticity is quite narrow, and actually our estimate of the efficient unemployment rate is actually also quite precise. So that doesn't seem, to affect the results too much. Another statistic for which there's quite a lot of uncertainty in the social value of non-work. So here what I'm showing you, so I said briefly earlier that we use two types of evidence to measure the social value of non-work. We have some papers that we use that uses administrative data on military people, and then we have a field experiment. And so here I show you the entire range of estimates that come out of this study. So a social value of non-work as low as 0. So that means that being out of work brings 0 contribution to welfare, and as high as 1/2. So that means that unemployed workers through home production and leisure, they are roughly half as productive as employed workers. And so you can see, of course, when the social value of non-work span all these values, the efficient, the efficient unemployment rate is going to vary. So the higher the social value of non-work, so the less costly unemployment, and so the higher the efficient unemployment rate. But all the key findings that I said earlier, that the labor market is generally inefficient, that the labor market is generally inefficiently slack, that the unemployment gap is high in bad times, all of these findings, they are going to remain even if you change your calibration of that estimate. So another kind of question that people may have is that here's the analysis that we have is quite static. So we assume that the labor market is always on the Beverage Curve, so the social planner is solving a static problem. But in the DMP literature, it's traditional to assume that actually the social planner takes into account the full dynamics of unemployment into account. So you assume that unemployment may deviate from the Beverage Curve, and unemployment follows the law of motion. When you compute the efficient tightness, the efficient unemployment rate under full dynamics, actually, it's not very hard. And the result of that social planner problem with dynamics is given by the Rosius condition. So when the Rosius condition is satisfied, you get the tightness and unemployment rate that are efficient with full dynamics taken into account. And here what I'm showing you is I'm comparing the efficient unemployment rate that come out of our sufficient statistic formula with the efficient unemployment rate that would be given by the Rosius condition. And what you can see is that, it's a little bit different, but the differences are very minor. So actually, dynamics, taking the dynamics into account, have almost no effect on the efficient unemployment rate and on the unemployment gap. But that's not very surprising, because we know that in the matching literature, we know that actually the unemployment is almost always on the Beverage Curve. The unemployment behaves as if it was almost always on the Beverage Curve, and the dynamics are not very important. And so that's why these two estimates of the efficient unemployment rate are so close. So finally, the last thing I want to show you is actually that our formula is, it's quite simple, and so it's quite helpful to see the welfare implications of other calibration. And so in particular, in the matching literature, a calibration that has received a lot of attention is the Hagedorn-Manofsky calibration for the social value of non-work. So to address the Schuyler puzzle in the DMP model, what Hagedorn and Manofsky proposed is that the social value of non-work is actually very, very close to labor productivity. So basically, people who are unemployed are almost as productive at the margin as people who are employed. And here I just want to show you what the implication of such calibration. So I use zeta, the social value of non-work, and I set it to 0.96, which is what comes out of Hagedorn and Manofsky's paper. And here's what you get. So if you put actually a social value of non-work that's so high, the efficient unemployment rate is very, very high. So it's always above 14%, and on average, it's 20%. So actually, if you set the social value of non-work to 0.96, like they do in Aguilar and Manofsky, you're working with a model in which the efficient unemployment rate on average is 20%. So that, that's possibly problematic, especially if you're doing policy work with your model. All right, so I think that's all I had to say. So maybe I'll wrap up and we can move to the next presentation.
Very good. Thank you, Pascal. So then second presentation will be by Leland Crane at the Federal Reserve Board, telling us about dynamic beverage curve accounting. So Leland, we now see your slides. Go ahead, you have 20 minutes.
Great, thank you so much. Yeah, and thank you very much to the organizers for including us and for everyone to attending. This is a really great session. So we'll talk about dynamic beverage curve accounting. This is joint work with HEJU, and since we're both at the Federal Reserve Board of Governors, the usual disclaimer applies that our opinions are not necessarily those of the Federal Reserve System. So I'll talk at the top about, just give you an overview about what we're doing in this paper. So we use an accounting identity to decompose the shifts in the beverage curve over time. And we really focus on three factors that can move the beverage curve around. Those are reduced form matching efficiency, out of steady state dynamics, and changes in the job separation rate. Most previous work has considered maybe one or two of these at a time, but part of what we're bringing to the table, we think, is the ability to look at all of them in a unified framework and look at them over time in each business cycle. And of course, there's an enormous literature that we're building on here that's partially listed at the bottom of that page. In terms of a quick summary of the results, what we find is that all three of those factors that I listed really do matter. Matching efficiency was very important in the Great Recession, but we find that at least so far, it's not that important for the current recession. Find that the job separation rate, at least in a two-state model, is also important across many recessions. And that the dynamics, the unemployment being out of steady state, is also important for understanding very sharp, sudden recessions like the Great Recession and the current one. So for today, I'm not going to try to cover all of that. I'll just try to focus in on 2 points. So one is in the context of a two-state model, I'll try to show how the job separations rate can distort the slope of the empirical beverage curve, and that relates to some of the discussion of the natural rate. And then I'll also talk in a bit more detail about the current recession and decomposing the shift that we've seen there. And what we find is that job separations and out of steady state dynamics were both very important, but as I said, matching efficiency doesn't seem to have played much of a role so far. Okay, so let me just give you like a quick overview of the model that we're using. We're very much looking at the labor market through the lens of a DMP model, and we're only going to be really leveraging some of what I hope are the less controversial assumptions. So the starting point is just discrete time, monthly data. Most of what I talk about won't have a participation margin, but we do have results for that as well. No on-the-job search for now, and we'll have Cobb-Douglas matching. And we're just going to try to express vacancies as a function of other stuff in the economy. And then we'll feed in counterfactual paths for things like matching efficiency and the separations rate, and see how that changes the path of vacancies. So all we really need to do our work is two things. We need the law of motion for unemployment, which is standard. The change in the unemployment rate is the inflows minus the outflows. That's in the top bullet there. And we also need the matching function, which the second bullet has written in terms of the job finding rate. So the job finding rate FT is matching efficiency sigma T times a function of the VU ratio. And there, alpha is the elasticity of the matching function. Okay, so when we rearrange those, we get this expression in the middle of the page. And this is something other folks have derived versions of this that we can't say this is original to us, but this is going to be the basis for our work. And this gives us, as I said, vacancies as a function of other stuff, including the level of unemployment. So we'll call this the beverage curve relationship. And if we think about fixing the level of separations in the other terms, then changes in U are movements along the beverage curve. So just to unpack that a little more, right, changes in U are movements along the Beverage curve. You can write out that it's a downward sloping relationship, and the slope of that relationship is basically pinned down by the elasticity of the matching function. So alpha over 1 minus alpha. Now, the other terms that show up in this expression are what we call shifters. So we think of those as moving the Beverage curve up and down, moving the intercept up and down. So separations ST, how does that play out? If we increase the separations rate, then you have higher vacancies for every level of unemployment, and the Beverage curve is shifted out. The labor market looks like it's operating less efficiently. Now, the opposite is true with matching efficiency. If we increase matching efficiency, the Beverage curve shifts down or shifts inward, and you have less vacancies coexisting with unemployment. And then that last term is the dynamics term. The delta UT plus 1 is the difference in the observed unemployment rate between tomorrow and today. Increasing the change in the unemployment rate shifts the curve down, or another way to think about it is that it's pushing vacancies below the steady state Beverage curve. This is what Pissarides talks about in the textbook, the like counterclockwise loops that you might expect to see. So let me talk through some of this in the context of some data. So what we've plotted here is the monthly log unemployment and log vacancies rates for the period 2001 to 2007. And this is a period when the Beverage curve was very well behaved in a sense. We don't see any real evidence of shifts or loops. And the regression line is there. So we have a downward sloping relationship with a slope of about -1. Now, if I add the Beverage curve that drops out of that identity I showed you, we get that red line, which is significantly steeper. So it actually has a slope of about -2. And this curve has been evaluated at the 2003 average values for job separations and for matching efficiency. So that pins down the location, and you can see that it's passing through the data in a period of high unemployment and low vacancies. So what explains this? How can we say that we're fitting the data when we have this really steep Beverage curve? Well, it comes down to what's happening in the shifters. So the job separations rate during this period actually fell significantly between 2003 and 2007. The job separations rate fell by about 20%. And what that did when we feed that into the identity is this Beverage curve shifts down from the red one to the blue one. So we have the same slope, the intercept has just shifted down as the job separations rate fell. And that blue line is the Beverage curve evaluated at the 2007 values. All right, so through the lens of this model, the flat empirical Beverage curve, or the relatively flat empirical Beverage curve, is the result of a movement along a relatively steep curve that's been shifting as time goes by because of changes in the separations rate. To give you a little more context, this plots the contributions of each of those shifters, not just separations, but also dynamics and matching efficiency. So the black line is like the net shift in the Beverage curve intercept. It's all been normalized to 0 in 2000. So you can see that black line is elevated around 2002, 2003, and then slowly shifts down. And the orange line, which is the contribution of separations, accounts for much of that shift. And the other terms are doing interesting things during recessions, but at least during this period, they weren't contributing much. Okay, so now I want to connect this to the previous paper. And we're really big fans of this paper. We've learned a lot thinking through the analysis and the interpretation. I don't think I need to summarize it because it was just explained very well. So what we're going to do is we're going to start from our estimated Beverage curve slope, and then we're going to do a similar kind of planner's problem. But we'll say at time t, the planner is going to assume that job separations and matching efficiency are going to stay constant at their observed values, and they're independent of policy. And that pins down the location of the Beverage curve that the planner faces. And then we'll plug this into the MS 2020 machinery in order to get the implied efficient unemployment rate. And we'll just adopt the cost parameters for vacancies and the social cost of non-work that they use. So this is the result of that exercise. The blue line here is the actual unemployment rate. The red line is a version of the MS 2020 unemployment rate using the Beverage Curve slope of about -1. And then the black line is what we get when we use our Beverage Curve slope of about 2. So our efficient unemployment rate is significantly higher than theirs. I think this makes sense. If we have a steeper beverage curve that the planner faces, then reducing unemployment is more costly in terms of the vacancies that you have to be willing to tolerate. And so the planner will choose a somewhat higher unemployment rate. So when we were thinking through this, I think the differences here really come down to the differences in the matching function elasticity, or the implied value of the matching function elasticity. We have reasons why we think our estimated elasticity makes a bit more sense in the context of this model. So we estimate alpha at about 0.66, and that's in line with estimates in the literature that only use hires from unemployment. They're right that their matching function elasticity is well within the range that's in the literature, but it seems to be closer to the estimates that use all hires. And there's no perfect solution here. I think the two-state model is a bit limited, and there's good arguments on both sides for which way to calibrate this. But I think the point that we want to make here is that the natural rate is sensitive to the beverage curve elasticity that you use, to whatever you think the social planner faces. But one point that I do want to bring up here is that in the context of a three-state model, it looks to us like some of these tensions disappear. Okay, so just very quickly, if we add a non-participation margin, we can rederive that identity. There's some extra terms floating around here, but N is the stock of non-employed workers, and we assume that they have some time-varying search intensity called Zn. And then we can redo everything we did before. We can estimate the matching function, but instead of using unemployed, we use searchers as the input to the matching function. So that's unemployed plus the discounted value of the non-employed. If we do that, we still get pretty good estimates. Our alpha is about 0.65, but it has a different independent variable. And then this is kind of the point we want to make, is that when we plot the empirical beverage curve, which is the dots, and then plot our steady state beverage curve that drops out of the matching function, they actually line up. It looks significantly better. So the steady state beverage curve, or that structural curve, is a lot closer to the empirical curve. And that means that in the context of this three-state model, these things like separations are playing less of a role and putting less of a wedge between the empirical beverage curve and the structural one that the planner might face. Let me see, I have to get to the back button, sorry. Okay. And this last slide here is just to say that even if we don't like the three-state model, even if we insist on using our elasticity, the MS 2020 results still hold if you think that job separations and matching efficiency that the planner faces would follow the same relationship that we see over the business cycle. So if the planner expects separations to be an increasing function of unemployment, then the empirical beverage curve would still be a good proxy for the structural curve that the planner would face. But like I said, we learned a lot going through the analysis and interpretation here, and we think it's a really brilliant contribution. But let me see, before I run out of time, I do want to talk some about the current recession, so the pandemic recession. And I'll show you how some of our results play out in the context of what we see now. So there's been some interesting things happening in the beverage curve. This was summarized by Catherine Rampel as the beverage curve is drunk. So here we've plotted some of the history. Normally the beverage curve may shift some, but generally there's a pretty tight downward sloping relationship. In the COVID shock, we did see unemployment jump way up. Vacancies fell only a tiny bit and haven't really adjusted all that much. So this is kind of unprecedented in terms of history. So we're going to do an exercise here where we're just going to compare 2 points. We're going to take a pre-shock average, which is the last half of 2019. This is a period of relatively low stable unemployment and also a pretty low job separations rate. And we'll compare that to a post-shock period. And this is going to be June to August 2020. And that, for the purposes of this, we're just going to skip over like April, March and April, where things were moving extremely fast. We could talk a bit more about what was happening there, but think of this as comparing pre-shock to the most recent history. And this period, so this post-shock period that we're defining is a period where unemployment is still very high, but also falling very fast. And the separations rates are also high, though of course not as high as they were, say, in April. So we'll calculate the steady state Beverage curve for these 2 periods. And then one by one, we're going to move those shifters from their pre-shock value to their post-shock value and see which ones contributed to the observed shift in the Beverage curve.
5 minutes.
Thank you. The order of the decompositions does matter somewhat, since this is a nonlinear function and we're kind of shifting a lot of things. In practice, we just take the average across all orderings, and it actually doesn't matter that much in this case. So just to show you visually what we're doing, the red line here is the steady state or structural Beverage curve that's passing through the most recent few observations. You can see August 2020 labeled there, so that's been the location of that Beverage curve is fixed off the most recent couple months of data. And we're comparing that to the blue curve, which passes through the pre-shock data. Okay, so what we get when we do that, remember we have these 3 factors, and we find that the out of steady state dynamics term is accounting for 65% of the shift. So the fact that unemployment is changing quickly is really important for understanding this. So that makes sense because pre-COVID, the change in the unemployment rate was roughly 0%. But in this post-COVID period, unemployment was falling by about 1% per month, which is an enormous change. So that's the biggest factor, is just simple out of steady state dynamics that we would expect. We expect the vacancies and unemployment to sort of oscillate around a steady state relationship when there's dynamics. It turns out in this recession, the dynamics are big enough to really matter. And then the second piece is the job separations rate. So we find that that accounts for about 35% of the observed shift. And that makes sense because pre-COVID job separations were about 1.5% per month. And those are significantly higher post-COVID, even though they're not quite as high as, they're much lower than they were in April. And the interesting thing we think is we find that the matching efficiency essentially accounts for nothing. We don't see any real changes in overall matching efficiency here. So I can just spend 1 minute showing that a little more clearly. So this plot is showing how we estimate the matching function. We have the log market tightness on the x-axis and then the log job finding probability on the y-axis. You see the black data is pre-2008, the blue data is 2008 to 2019, and the red dots are the 2020 data. So you can see that the 2020 data lines up pretty well with the historical series, with the exception of this one data point, which I think is April, which is wandered off. But changes in overall matching efficiency would show up in changes in the intercept. And with the exception of that one data point, we just haven't seen like a shift downward in the matching function. So that, that suggests to us that matching efficiency hasn't really changed overall. There's been other papers that have done a good job of parsing out temporary unemployment versus permanent unemployment and how those two groups differ, but we find that overall it kind of nets out to no change. Yeah, so just to summarize, no evidence of mismatch. In a sense, the Beverage curve is exactly where it should be, given the observed elevated rates of job separations and the fact that the unemployment rate is just changing really, really fast. Okay, so just to wrap up, we, in the paper, which we're working on a revision for, we provide a quantitative decomposition of the Beverage curve, We find, I couldn't get to all of this, but we find that the matching efficiency was important in the Great Recession, so far not in the pandemic recession, and that the out of steady state dynamics and job separations are really important. There's a lot more we couldn't quite cover today. We have results for other recessions, a little more looking at out of steady state dynamics, especially we think that also played a role in the Great Recession. And of course, the three-state model, which I touched on briefly. That's all I have. So thank you.
Thank you very much, Leland. So our third presentation is going to be Aysegul Sahin at the University of Texas, Austin, telling us about the unified approach to measuring U-star. We see your slides. Aysegul, okay. Go ahead. You have 20 minutes.
Do you hear me?
Yes.
Okay, well, thanks so much to Emmanuel for putting together this session. Really, all the papers are so closely connected. I don't even have to talk about half of my paper. So thanks a lot for setting the stage for my presentation. First, I'm going to talk about the unified framework that we developed in 2019 with Richard, Stefano, and Mark to measure the U-star. And then I'm going to give you an update of the natural rate in COVID times. So the concept of the natural rate that we are estimating here is slightly different than the ones we have seen. So the concept is the unemployment rate such that controlling for supply shocks, inflation remains stable. So I'm bringing back inflation into the picture when I talk about the natural rate. And what differentiates us from the extensive literature on this topic is our use of two key inputs. The first one is using unemployment flows by demographics, which will help us pin down the secular trend of unemployment. This follows Regis's work with masters. And the second is using inflation expectations, both short-term and long-term, to inform us about current and future unemployment gaps. So it's always good to start with a quote from Friedman. In his 1968 presidential address, he said that when he mentioned the natural rate, he did not suggest this is immutable or unchangeable, and that's what we are all talking about. And he speculated that improvements in employment exchanges, availability of information about job vacancies, labor supply would affect the natural rate. And what we are doing in this paper is a modern take on his insight. And essentially, what we are doing, bringing in rich data, both on the inflation side and both on the labor market side, to bridge the gap between the Phillips curve literature and the macro labor literature that typically relies on microdata. So what we specifically do is we first identify a slow-moving, unmistakable secular downward trend in the unemployment rate, and this is solely driven by the decline at the rate that Americans are becoming unemployed. So essentially, we call this a decline in unemployment inflows. And in the paper, we have very detailed analysis of these factors that are driving that. Up until 2000, this was the grand gender convergence, which reduced inflow of women into unemployment because of factors related to childbirth and maternity. And after 2000, this secular trend is driven by the declining business dynamism, which reduced job destruction, and also the slow-moving demographic trend, the dual aging of both workers and firms in the US economy. Once we identify this secular trend, we take this into a new Keynesian Phillips curve framework and estimate a forward-looking new Keynesian Phillips curve for the last 60 years with one-time invariant slope. And we show that incorporating short and long-term inflation expectations, even with a unique slope, actually reconciles the joint dynamics of unemployment and inflation that we observed in the last 60 years. And then one other thing it's very related to what we have seen in the previous paper is that these U-star estimates that I will get, I can easily compare with the microdatabase ones, and I'll show you that they align really well with mismatch unemployment that we can measure in detailed vacancy and unemployment data. And in terms of numbers, what we find, I'm going to do first pre-coronavirus, as we all did. At the end of 2019 Q4, unemployment was at 3.5%, and our natural rate estimate was at 3.8, with a range of 3.5 to 4.2. And because of the secular trends, we saw little upside risk on U star absent the recession. And post-coronavirus, as you know, there was this huge spike in the unemployment rate in April, which reversed pretty quickly. And our estimate for U star currently is 0.2 to 0.7 percentage points higher than its pre-COVID level. So it puts our estimate to 4 to 4.5%. And I'll show you an updated measure of skill mismatch, and you'll see that this is pretty much in line with what we measure in the data, and also with the previous paper that we have seen. So let me set the stage by a very simple unemployment decomposition that is easy to relate to the concepts I'm going to talk about. So this is the unemployment rate. It is driven by its secular trend, which is related to slow-moving factors such as demographics or labor supply changes. And then there is the unemployment gap, which is typically the object that the monetary authority is interested, the deviation of the unemployment rate from its natural rate. And on top of it, there is yet another factor that we talk about, which is the persistent deviation of the natural rate from its secular trend. So essentially, what we think of the natural rate is it's the sum of its time-varying secular trend plus these persistent deviations. And of course, these persistent deviations are affected by the shocks that the economy goes through, recessions and that. So what we do is we estimate the secular trend by using detailed labor market flows, and then we use a new Keynesian Phillips curve and estimate it using this secular trend plus inflation expectations data and come up with a U-star estimate. So now let me jump to the secular trend in unemployment. We all talked about the flow dynamics of unemployment, but this is a true state abstraction. Inflows are people who become unemployed, outflows are the ones who leave unemployment. So I'm going to use data by age and gender, and I'm going to model flows jointly using a state space model. Again, this is a follow-up of Barnichon and Master's work. And I'm going to allow for common business cycle component and estimate group-specific trends. So for each age and gender group, we're going to estimate different business cycle and trend components for both inflows and outflows. And then once I have this, I can aggregate them up and come up with the trend versions of these inflows and outflows. And then I can use the simple steady state unemployment equation, as Pascal said, which is pretty much almost always satisfied, to get back to the secular trend of unemployment. And this also takes into account changes in the composition of the labor force, because I'm using time varying weights for each age and gender group over time. And this is the inflow rate into unemployment, and it has an unmistakable trend, as you can see. And this is the trend that we estimate by separately estimating trends by demographics. And it used to be around 4%, and it has been declining to almost 2%. And this downward trend continuing despite the big spike that we observed during the Great Recession. And this is the outflow rate. Of course, its procyclicality is way more pronounced, but the trend that we estimate is very subtle. It only adds about 50 basis points to the unemployment rate if you think about its effect. And putting it all together, this is the secular trend of unemployment that we estimate. It increased throughout 70s up to 7%. There was a big drop up to 1990, and it was constant in the 90s, around 6%, and since then it has been increasing. And these are the 68 and 95% coverage intervals. So in terms of the drivers of this, I don't have much time, But if anything, the outflow rate is pushing up trend unemployment rate. But the downward trend in the inflow rate is so prominent that it's driving the trend unemployment rate down. And in terms of the demographics of it, before 1996, women and young workers account for much of the decline. This is when women became more attached to the labor force and the baby boom cohort started to age. However, after 1996, we see that this decline is common to all demographic groups. And that's one of the reasons why we relate this to the dual aging and decline in business dynamics. So now that I have this U-bar, the secular trend of unemployment and its distribution, I can move on to estimating the new Keynesian Phillips curve that we derived following Galli's work. So the new Keynesian wage Phillips curve, wage inflation is driven by mean real wage growth that we get from the data, drift in long-term inflation expectations, pi t star, that evolves according to a random walk, and current unemployment gap. Remember that we define as UT minus UT star, which evolves according to an AR2 process. And you can see here that in addition to the unemployment gap today, I also have the expected future unemployment gaps. And if I look at this equation one period forward, you see why inflation expectations are informative about XT, because they reflect expected future XTs in this framework. And you can get a similar Price-Phillips curve in Galli's framework, again, reflecting this connection between expectations and unemployment gaps. And in our framework, we use actual data on short-term inflation expectations, which are informative about these XTs in the future, and long-term inflation expectations that are informative about this pi t star. So we estimate this model using Bayesian techniques, and in terms of inputs, we have price and wage inflation. There's always a debate in this literature which wage series to look at. We look at all 5, and we consider them as noisy measures of the real underlying labor costs. And we use inflation expectations data 6 months ahead and 5 to 10 years ahead. And on top of it, this U-bar, the secular trend of unemployment, and the uncertainty around this is an input to our estimation process. So now let's look at how U-star looked in the last in the last 60 years. This is the unemployment rate. Again, I'm not showing you the COVID-19 recession yet. And this is our estimate of the natural rate. So you can see that there was a big increase in the 70s, up to 8%. And unemployment rate was below its natural rate for a very long period of time, consistent with the inflation that built up during that time. And this is the Volcker disinflation, and we see big unemployment gaps opening up. And then the natural rate gets down to around 5%. There's an increase in the natural rate during the Great Recession, but it's around 1 percentage point. It's much smaller than the level that we have seen in the 1980s. And if we look at the last couple of years before the recession, you see that the natural rate was around 4%. And the year before the recession, we were actually able to go down the natural rate, with unemployment being below, around 3.5%. So even though the concepts are different, this behavior is very similar to what we have seen in Emmanuel and Pascal's paper. And if you want to see the relation with the secular trend, this is what we are seeing. You see that the secular trend anchors unemployment movements, natural rate movements, but there are very persistent deviations between the two. So one last thing before I talk about COVID-19 is the importance of inflation expectations, because I told you that unlike many papers, we have one single slope for 60 years of data that seem to capture the joint behavior of unemployment and inflation well. So a good comparison is 80s and 2000s. So this is the Great Recession and this is the 1980s. So the unemployment gap that we measure is very similar, 3.5 and 4 percentage points, really big unemployment gaps. But if you look at the behavior of inflation, in the 1980s, the decline is 4.5 percentage points. In the Great Recession, it's only 1.3 percentage points. So the missing this inflation. So the way we reconcile this is by the differential behavior of inflation expectations. There was a dramatic drop in inflation expectations in 1980s, while in the Great Recession, there was only a mild decline in inflation expectations. So by letting inflation expectations be a part of our estimation process, we are able to capture this without resorting to changing the slope of the Phillips curve.
5 minutes.
Perfect. So you start in the time of Corona. This is the quarterly unemployment rate. So as you know, from March to April, unemployment almost quadrupled. And this is the quarterly one that peaked in Q2 at 13%. So I have been pushing for the fact that looking at flows are always informative in understanding unemployment dynamics. So now let's look at the inflow rate and outflow rate starting in 2015. And these are quarterly. So you can see this big spike in the unemployment rate, which is almost reverse. And this is the outflow rate. It declined a lot, but the decline was not as bad as the Great Recession. But now let's take out temporary workers on temporary layoffs. So what you see is that a barely increase in the inflow rate, but of course, since these workers left unemployment relatively fast, they actually didn't reduce matching efficiency. If anything, matching efficiency looked like it increased. But if I take them out, there's a bigger drop in the job finding rate. So we think that this is a more useful picture to think about the natural rate, because we are trying to understand medium-term movements in the working of the labor market when we think about the natural rate. And the other thing is that there is a bit of a change here. There is really no change here relative to 2019. So whatever is going to affect the natural rate, it should come from the outflow rate. So now, motivated by this, I'm going to estimate the natural rate with our model using 3 different unemployment rates. The first one is the official one, peaks in April. The second one is going to just say that, okay, I know these are temporarily unemployed people, but they are becoming permanently unemployed, some of them. So let me just put a trend that looks like this, a gradual increase. But in this case, you are shifting the peak because you are really trying to capture them when they are permanently unemployed. And the third one does this more explicitly. It takes out temporary layoffs from the unemployment rate and consider that unemployment rate in the context of the model. So what do we see in terms of the rise in U star? So if I use this big spiky unemployment rate with this unprecedented increase, I foresee a 3 percentage point increase in U star, but it reverses very fast. And the increase is only 0.7 percentage points. If I use the gradual increase, it's 0.5 percentage points increase relative to 2019 Q4. If I use the alternative where I take out temporary layoffs, it's only a 20 basis points increase in U star. So regardless of the measure that we are looking at, the rise that we have is less than 1 full percentage points. So the last thing I want to do is, but this is a model. Does it know anything about whether this is COVID, people cannot find jobs, economy is shifting? So what I can do is I can calculate mismatch unemployment. And Leland alluded to this, but he did not use this measure. So I can look at the effect of the increasing disconnect between skills of unemployed workers and required skill of vacancies and calculate how much unemployment increased because of that. So it's the first constraint, first best equilibrium, somewhat related to, again, what Pascal talked about, because I'm still respecting the frictional nature of unemployment in the economy. And you can see that, perfect, the increase is way, way less than what we have seen during the Great Recession. And when I compare my natural rate estimates with what I get when I calculate skill mismatch unemployment using industries or occupations, I get 0.30 to 0.50 percentage points increase in mismatch unemployment. So the bottom line is that the increase seems to be less than 1 percentage point, and our preferred estimate, which perfectly lines up with skill mismatch for U-star, currently is 4.2, with a range of 3.9 to 4.7%. The last thing is that all these secular factors that we identify are still affecting the economy at the background. Thank you.
Thank you, Aysigul. So let's move now to our last presentation by Hee-Ju Han at the Federal Reserve Board about duration structure of unemployment hazards and the trend unemployment rate. Hee-Ju, go ahead. You have 20 minutes.
Okay, thank you. So you can hear me, right?
Yes.
Okay, great. So I thank the organizer for including this paper to the program. The title is The Duration Structure of an Unemployment Hazard and the Trend Unemployment Rate. The user disclaimer of the Federal Reserve System applies. So this paper develops a new method to estimate the trend unemployment rate that takes into account the time-varying duration profile of unemployment hazard. The duration profile of unemployment hazard is characterized by 3 time-varying factors: level, slope, and curvature. And I'll call this as the duration structure unemployment hazard. Okay, and then I introduced a new concept called the duration structure trend unemployment rate, or DSTUR. The definition is the unemployment rate that is composed of the trend components of the time-varying parameters constituting the duration structure of unemployment hazards and the trend inflows to unemployment. The identification of the trend unemployment is achieved not only from the trends in the labor force flows, but also from the low frequency changes in the distribution of unemployment duration. So here are the key findings. First, the DSTUR exhibits a secular decline between 1980 and 2000 and a slow uptrend during the 2000s and a decline between 2011 and 2019. The slow uptrend during the 2000s mainly reflects the secular rise in long-term unemployment that more than offsets the downtrend in the inflows to unemployment. Second, without taking into account the mismatch or the extension of unemployment insurance benefits explicitly, the DSTUR still can capture the slow rise and fall in the trend unemployment rate during the period surrounding the Great Recession. Next, when we take a look at the DSTUR by the duration components, the short-term components has trended down since 1980, while the long-term component shows an uptrend during the 2000s, which likely implies the falling frictional unemployment and the rising structural unemployment. And last, the short-term unemployment rate gap exhibits a strong Phillips correlation with the PCE inflation. Okay, so what is the duration structure of unemployment hazard? Now you're looking at the unemployment exit probabilities by the duration of unemployment in the left panel. The uppermost line is the exit probabilities, the monthly unemployment exit probabilities of those who've been unemployed for 1 month, 2 to 3 months, 4 to 6 months, and longer than 6 months. As you can see here, hazard declines as an individual stays unemployed longer, and this phenomena is referred to as the negative duration dependence. So if you take a look at the snapshot of a certain period of time, the duration profile of unemployment continuation probability shows this upward sloping curve. Okay, so let me talk about the right panel. The y-axis is the monthly probability, for an individual to stay unemployed next month, and x-axis is the duration of unemployment in months in progress. Okay, so the negative duration dependence is captured by this upward sloping curve, and this upward sloping curve is characterized by three factors: level, slope, and curvature. Here, the curvature is the difference between the black line and the blue line. The level factor captures the unemployment continuation probability of newly unemployed workers, and the slope factor captures the overall deterioration in unemployment hazards, and the curvature factors captures the non-linearity between the unemployment continuation probability and the duration of unemployment. Okay, so I use the Laguerre function to model the nonlinear duration profile of the unemployment continuation probability. Okay, then what is the Laguerre function? It's the function that is actually used to model the term structure of interest rate in Nelson and Siegel's model. Okay, it's the function that is used in the finance literature. So the Laguerre function is used to model the temporal dependence of a variable. So for example, in Nelson and Siegel's term structure model, F tau is the forward rate of a bond with maturity tau years. Okay, and it is expressed into the linear combination of the level, slope, and curvature factor. So the level factor is 1, and it captures along with the factor loading beta 0, it captures the long-term interest rate, and the slope factor is captured by this exponential function, and the curvature factor is captured by this polynomial multiplied by exponential function. And the parameter lambda, captures the the lambda, captures the optimum of the curvature function. Okay, and these, betas are the factor loadings on the level, slope, and curvature factor. Okay, so I essentially use the same idea to model the duration structure of unemployment hazard. So here, xt tau is the factor that determines the unemployment continuation probability of those who have been unemployed for tau months in month t. Okay. Here, tau is the duration of unemployment, and t is the month, for time. Here, the factor xt tau is composed of the level, slope, and curvature. And here level is 1, which is omitted, and the level captures the unemployment continuation probability of newly unemployed workers, and the level is determined by the factor loading beta 0. Okay, and the slope here factor is determined by this exponential function, and the factor loading is beta 1t. Okay, the factor loading on the slope factor determines the overall deterioration in the unemployment hazard throughout the duration. Okay, and the curvature factor here is the polynomial multiplied by exponential function, and here the vector loading beta to t captures how pronounced the curvature is, or the relative speed of deterioration in unemployment hazard among short-term unemployed relative to the speed of deterioration in hazard among long-term unemployed. Okay, so here lambda t's essentially captures the optimum of the curvature, or the months in unemployment where this nonlinear pattern starts to kick in. Here I make one assumption, that is an individual's unemployment exit probability does not change once an individual has stayed unemployed longer than 1 year. Okay, and this assumption is consistent with the external experimental evidence from the Croft-Lange and Norwidington. So that means that once tau is equal to or greater than 1 year, the xt tau factor is expressed into the sum of the level and slope. As you can see here, all the parameters are allowed to vary over time. And then I'm going to talk about the identification in 2 slides. Okay, here are the data that I used in this analysis. UT1 is the number of people newly unemployed in month T. Okay, so it means that with the duration 1 month. And UT23 is the number of people who are unemployed for 2 to 3 months. And UT46, UT712, and UT13 plus is the number of people unemployed for longer than 1 year, 13 months and over. So I collect these 5 data points in the vector YT, and the sample period is from 1976 to 2019. I do not consider the COVID period. Okay, identification. The identification of the parameters are based on the dynamic accounting identity from Anne and Hamilton 2020 paper. Just to give you the intuition of what's going on, I suppress the time subscript. The economy is in the steady state. So U1, the number of newly unemployed worker, is equal to the inflows to unemployment. Okay, so it's the inflow. And here, little p tau is the probability to stay unemployed next month of those who have been unemployed for tau months. Okay, it's a double exponential function of x tau, and I use this double exponential function to ensure that the probability to fall, between 0 and 1. And this is, just a usual functional form that is used in the proportional hazard literature. Okay. Here, big PK is the probability to stay unemployed for K consecutive months, and it's the product of, K monthly unemployment continuation probability, which makes sense. Okay. So let's take a look at U23. It's the number of people unemployed for 2 to 3 months, and is equal to U2, the number of newly unemployed people multiplied by the probability to stay unemployed next month, plus U3, the number of people newly unemployed multiplied by the probability to stay unemployed 2 more months. Okay, so we are essentially doing the accounting identity exercise. And the same logic applies for U46, 712, and 13 plus. Here, I assume that the maximum duration of unemployment existing in the economy is 4 years. Okay, so we have 5 data points and we have 5 unknowns. W, the factor loadings, beta 0, 1, 2, and lambda. So we have 5 equation, 5 unknowns, and we can identify the time varying parameters. Okay, the actual model that I consider in the paper is the dynamic one. So we bring back our time subscript back, to the model. And here I make one more assumption, that is each data point is observed with a measurement error. Here little r's on the right hand side. Okay, and everything else is the same as the accounting identity model. And then I make assumption that the vector RT, that is the vector composed of the measurement error, is drawn from a normal distribution with mean 0 and covariance matrix R. So this means that the accounting identity model that I just described 2 slides ago can be cast into the measurement equation of a nonlinear state space model. Okay. Now let's move on to the state equation of the state space model. I make another assumption, that is the latent dynamic variables evolve smoothly over time following a random walk, which is a standard assumption in the literature. And here epsilons are the innovations. If I collect the 5 latent variables in the vector CT and the error, dynamic innovation terms in epsilon T vector, then CT evolves according to a random walk, and epsilon T is drawn from a normal distribution with the mean 0 on covariance matrix sigma, which is a standard assumption. And here this is the structure of sigma. So the distribution of unemployment duration in month T is shaped by the history of labor force flows. That means that we need to take into account the joint distribution of latent variables when we think about the state space model. So we have this big state equation, and again we have a nonlinear state space model, meaning that we form the likelihood function and make inference on the latent variables using the extended Kalman filter. Okay, so here are the estimated level, slope, and curvature. Okay, the level factor is 1. Here's the black line, and the slope factor is the red line. You can see the upward slope, and the curvature is, here is captured by the dashed line. So these are the estimates. When lambda is estimated to be 1.94, which is the average of the sample. Okay, and you can see that when duration is 10 months, there is a apparent nonlinearity. Starts to kick in. Okay, so here are the factor loadings and the inflows and lambda. So here, now you're looking at the factor loading on the level factor. So essentially, you can think of this beta zero estimate to represent the unemployment exit probability of newly unemployed workers with the duration 1 month, and not the average unemployment exit probability. Okay, so it shows a clear, procyclical pattern, which makes sense. And we can see that there is a downtrend, and this, beta zero has trended up in the past 10 years consistently. Okay. And the factor loading on the slope factor doesn't really show any particular trend or cycle. And the factor loading and the curvature factor, as you can see here, shows a procyclical pattern, meaning that the unemployment hazard of the short-term unemployed deteriorates much faster relative to the hazard of the long-term unemployed during an economic downturn. That particular happened during the 1990s recession and during the Great Recession. As you can see here, there's a slow-moving component in beta 2, and it is notable that the beta 2 dropped a lot during the Great Recession. It improved, and after the Great Recession was over, but it didn't really recover to the pre-Great Recession levels. Okay, and we see this downtrend in inflows, which is mentioned by Isegel. Here, note that I'm talking about the number of newly unemployed workers. So the unit here is in million workers. And as you can see here, the lambda parameter doesn't really show any particular trend or cycle. Okay, these are the monthly unemployment continuation probability by the duration implied by all the time varying parameters, but let me skip this. Okay, now we are ready to talk about the duration structure, trend unemployment rate. Again, the definition is that unemployment rate that is consisted only of the trend components of the time varying parameters. But I'm going to use the level of lambda as it is because lambda doesn't really show any trend or cycle. Okay, so it's a two-step procedure. Okay, I first extract the trend components of the 4-parameter and the feed trends back into the accounting identity model to recover the trend unemployment. And then I divide the trend unemployment by the trend labor force. Okay,
5 minutes.
Thank you. And to extract the trend components, I use the standard Bayesian trend cycle decomposition technique specified in quarterly frequency. So here I assume that, for example, in the case of inflows, and I assume that the inflows in quarterly frequency follows an I2 process, means that the inflow is composed of the trend and cycle. And the trend of the inflows has this, time varying, growth component that evolves according to a random walk, meaning that the difference trend, evolves according to a random walk. Okay, and and also cycle, is assumed to evolve in the AR2 process, which is standard. Okay, I essentially use this same model to extract the trend of the rest of the time varying parameters. Okay, so here are the trend estimates. Now we are ready to take a look at the result, the estimated DSTUR. The red line is the estimated DSTUR, and the black line is the unemployment rate, and the blue dashed line is the CBO's unemployment rate. So as you can see here, during the 1980s and 1990s, DSTUR is a bit higher than the CBO's short-term natural rate. They kind of converge in 2000. So let's take a look at what happened during the 2000. So during the 2000, the CBO's short-term natural rate continued to go down. However, the DSTUR gradually, go up. It's because the downtrend in the inflows, the influence from the uptrend in long-term unemployment was more than offset, the downtrend in the inflows to unemployment. That resulted in, the slow uptrend in the STUR on net, during this period. So both series reached their peak in 2011, and then both trended down. So actually, the STUR and the 2019 at 4.0%. Okay, here the key takeaway is the low frequency variation in the distribution of unemployment duration is helpful in identifying the trend unemployment rate. Okay, now you're looking at the duration components of the DSTUR. Okay, the red line is the DSTUR with the duration 1 month, so short-term DSTUR, and the black line is the DSTUR with duration longer than 6 months, so essentially long-term DSTUR. You can see that there are two different trends going on within the trend unemployment rate. Okay, so this decline in short-term trend unemployment rate, might imply the decreased friction unemployment, and this rise in the, long-term DSTUR might, imply the increased structural unemployment, meaning that the composition of the trend unemployment might have changed over time. Okay, so lastly, I explored the implications for the Phillips curve using a simple Phillips curve model, where the 4-quarter changes in the PC inflation is a function of the unemployment rate gap, gap in the unemployment and DSTUR, and its lags and inflation expectation term. Okay. So instead of this aggregate gap, I also consider the duration components of the unemployment rate gap. Now, here are the key results. The short-term unemployment rate gap with the duration less than 6 months, less than or equal to 6 months, has a strong Phillips correlation with the PC inflation, while the Phillips correlation with the aggregate gap is small. Okay. When we replace the unemployment rate gap with the unemployment rates themselves, by the duration, none of the Phillips correlation coefficients are statistically significant, meaning that when we consider the right unemployment rate gap in the Phillips curve is stable and is there. Okay. I just summarized the estimation results here. One thing that I'd like to bring your attention is that the Phillips correlation of the long-term unemployment rate gap is small relative to these Phillips correlations on the short-term gaps, and also not statistically significant. So meaning that when we think about the unemployment rate gap by the duration, some components have implications for inflation, but not all of them has implications for the inflation.
1 minute.
Okay, so let me conclude. It's perfect. So this paper introduces the duration structure of unemployment hazard and develops a novel method to estimate the trend unemployment. And here are the main takeaways. First, the identification of a trend unemployment rate is not achieved not only from the trends in labor force flows, but also from the low frequency changes in the distribution of unemployment duration. And we just saw the secular decline in the short-term trend unemployment, but secular rise in long-term trend unemployment, meaning the decline in frictional unemployment rate and rising structural unemployment rate. Last but not least, we just observed that the short-term unemployment rate gap has a strong Phillips correlation with the PC inflation. Thank you.
Thank you very much, Hiju. So let's now move on to Régis Barnichon, who is going to be our general discussant. Unmute yourself.
Okay, can you hear me?
Yes.
All right. Thanks very much, Emmanuel. So thanks a lot for inviting me to discuss all these 4 papers and this very interesting session. So I've never discussed 4 papers in one go before. So let me see. So what I tried to do in the discussion is to give kind of a broad overview of where those 4 papers fit and where we're trying to achieve and the kind of questions we're trying to answer. So why first, I was asking, why first should we look at some unemployment gap? Okay, well, there's a number of questions that are of interest to policymakers or economists more generally. The first one is the unemployment is a very good cyclical indicator. At least it is used as a cyclical indicator. And so a gap gives you an indication of where you stand in the business cycle. That's the first idea. Now, more maybe interestingly, it allows you to assess, given the current level of unemployment, the gap gives you an indication of whether it's sustainable. So for practitioner, fiscal or monetary policymaker, gives you an indication, again, where you are in the cycle and whether this level you're seeing is likely to continue. And going a bit deeper with this range of questions, well, actually it also gives you indication about where inflation is going from the Phillips curve relationship. So you can use the unemployment gap to predict inflation. And that is interesting, especially to monetary policymakers, so central banks that have an inflation mandate. Another one, which is the employment gap, is useful because a lot of central banks have either explicitly, like the Fed, or implicitly some economic activity mandates, say like full employment. And so the Fed, say, would have an employment level, unemployment target, and so it allows you to assess how far you are from your target. Okay. And then the last question, which would be, okay, what should be that target? Okay, so that practitioner's target, or that the target that Congress or some sort of the elected body would provide to the policymaker, what should be the target? And that's kind of what is the optimal level of unemployment. What should be the target for the unemployment level? So the gap tells you how far you are from that. And so depending on the question, you're going to look at different concepts for what we call U star. So this gap is U minus U star. And so there are different concepts in the literature because they have different questions that we have to. The first one I'm going to call it, so I'm going to use different notations than typically in the literature to make it extra clear that I'm looking at different concepts. And so that way it should be intuitive. That the first one is the long run level. So ULR, this is just a long run level of unemployment, meaning the level of unemployment once business cycle fluctuations have died out. Okay, so if there were no business cycle fluctuations in the world, this is where unemployment would be. Okay, and so two of the papers today, Crump et al. And Ann, talk about this. Okay, so what is the long run value of unemployment? The second one, and related to the question about predicting inflation, or for a central bank with an inflation and employment mandate, what is the stable inflation level of unemployment? So I call it U pi star. So you could think about it with the Nairo. This is anything that is a Phillips curve based estimate of unemployment. So on unemployment, whenever you're below it, inflation goes up. And the third one, and that's the paper by Mishaya Saez and then Adam Crane, looking at what we should target in a way. Okay, so what is the efficient level of unemployment? So you call it U-opt, okay? The unemployment that maximizes social welfare. So in the discussion, I'll discuss the three kind of methods we have to measure those three concepts. All right, so I'll start with measuring long-run unemployment. So the identifying assumption here, it's always in the background, even if it's not, I think if it's not explicitly acknowledged, is that the longer unemployment is a slow-moving object, and we need to make that assumption. And so the naive approach was not that naive. That's the one we used to do. It's just, well, you just use a low-frequency filter on the unemployment. Okay, so you take an HP filter, backslooking, you look at unemployment, you take something that's slow-moving, like boom, that's the long-run unemployment. A slightly fancier version of that approach, which is called a forecast-based approach, is the long-run unemployment is just the forecast of unemployment at some horizon. So you use a time series model, so it could be an AR, it could be a VAR, and it has time varying parameter. And then at each point in time, you're going to say, okay, where is unemployment going to be 10 years from now? Say, I mean, 10 years, it's arbitrary. It could be infinite, it could be 20, 55. I mean, it has to be practical, but that's the idea. So you use that time series model to kind of get a sense of what unemployment is moving towards to in the long run. Yeah, it's a little cleaner in the sense it's a bit more structured than this naive approach, because it corresponds more exactly to this forecast based to this concept of a long run unemployment. And more recently, so we've started looking at there's a big literature looking at the flow, the composition of unemployment rate, because the flows can have really interesting things to teach us about the properties of unemployment. And using this flow-based decomposition, we can get a finer, I'll define finer in a second, estimate of unemployment movement. So there's this accounting identity, and to a first order, it gives you this, and Aigigul and Pascal, I mean, we've seen that many times before, that change in employment are kind of like moving linearly with change in separation rate and change in job finding rate, or outflow rate rather, sorry. So the movements in and out of unemployment, looking at those two flows gives you movement and employment. And the idea of doing this decomposition, at least the way I understand it, is that, well, you can apply this relation to a long-run concept, since it's an identity. And the idea underlying this decomposition and predicting the long-run employment from those two flows is that if And that's if the time series properties of the separation rate and the finding rate, or unemployment inflow rate and outflow rate, are different, then you might get a better forecast of the long run value of unemployment by forecasting the two objects separately. So that's a common property when you do forecasting, that it's better to disaggregate the series if the time series underlying the object of interest have different properties. If that's the case, you might get a more precise, a more accurate forecast. The trade-off, of course, is that as you disaggregate data, you get more noisy measures. Okay, so the underlying objects you're now forecasting are more noisy. And that's just like always in statistics, you have this usual bias variance trade-off. So the idea here is like, okay, I'm going to decompose unemployment in two flows and forecast those flows separately, hoping that I get a better forecast because they have different time series properties, and hoping that the extra measurement error is not going to mess up my forecast too much by increasing the imprecision of the forecast. And so just to give so this is a picture that I picked from I.G. Gould's paper, and this is the inflow rate and alpha rate, and it goes with the idea that they do seem to have really different time series properties. So the inflow rate is a very strong secular trend. It's a lot more skewed. It's skewed like upwards, so it goes up. It can go up very quickly. And the outflow rate doesn't have a trend. So there's good arguments for doing this exercise. Okay. And so the contribution of Anne's paper is to do that long run forecast by doing this accounting identity where you forecast separately separation rate and finding rate. But in addition, to have a richer model to understand the job finding rate, the outflow rate FT. And the idea is that we know that the longer you're unemployed, the less likely you are to exit unemployment. And therefore, you can disaggregate that object further. And so the idea that, again, if the underlying components of FT have different time series properties, you might get a better forecast of FT long run if you split it up again. So that is the same idea going forward that Anne is doing, is that while you do this accounting identity, and then this object, you model the duration dependence with some Nelson-Siegel function, so level slope curvature, like in finance, the term structure modeling. And then if you model this, then maybe you can get better forecasts of that object FTLR, and therefore a better forecast of long run unemployment. Okay. A bonus of doing this also, and a bonus of doing this, the flow decomposition, is that also gives you some better interpretation of where the trend in unemployment is coming from. And especially in Anne's paper, you get a better idea. So is it the long run unemployed, or is it the short-term unemployment that having this structural change? Okay, so the second part, how about you measure? So if you're interested in predicting inflation or knowing what is the stable inflation unemployment rate, how do you measure this object? So it starts from a Phillips curve. So here I wrote down a simpler Phillips curve than they have in the paper, but that's the very standard one. And the idea is you're trying to get that object, Ut by T star. And the idea is very simple. Whenever you see inflation going up, controlling for everything else, it means unemployment is below its U pi star value. Okay, and so whenever you see that inflation is stable, it means unemployment is that it's pi star should be a pi here value, and that's how you can infer that Ut pi star value. Okay, now you need again an identifying assumption here, and that's the same one as for the long run unemployment, is the fact that to separate that unobserved Ut pi T star from the cost push shock, you need to kind of separate them. And to do that, we say that this guy is slow moving. So that's a common assumption. Again, the NIRU, if you want, or the inflation, stable inflation unemployment rate is a slow moving object. And with that assumption, you can separate ET, the disturbance, from that object of interest and identify it. I just want to add a comment here, though, is that there are a lot of endogeneity issues in this Phillips curve. I just list three from this review paper by Mavridis and co-authors that I think we need to address seriously in this Phillips curve estimation. So the first one is confounding from cost push shock. So even if you do this identifying assumption that that long run concept of U pi T stars is slow moving, to to estimate that kappa consistently, so the slope of the Phillips curve consistently, you need IV, because otherwise you're going to have confounding from those cost per shock. So that's the first endogeneity problem. The second one is pi t star. So pi t star is some forecast of inflation. So IJGold to use these two separate ones. So that gives a lot more information. That's great. The thing is that this is measured with measurement error, so that gives you an endogeneity bias again. All right, and that guy being unobserved, that gives you another problem. Okay, but that's so typically you would want to use IV to estimate this kind of relationship. Okay. And so now, what is the further innovation by IJGold's paper was to relate those two concepts, the long-run unemployment and that stable inflation unemployment concept. And the idea that those two guys, they are both slow moving and they kind of cannot diverge too much one from each other. Okay, so there are one basically relating the two. And so by using the flows, okay, given the explanation I gave before, so why using the flows can give you better identification of UTLR, using this relationship, you can a more precise estimate of that stable inflation unemployment. Okay, and again, you get a bonus because you use the work of flows to estimate longer unemployment, and therefore you can better interpret any trend you might get in that stable inflation unemployment rate. So same idea. So this is nice in a unification in the paper. Okay, I'll just say I don't know in this particular paper, so it's not at all an attack on this paper. It's just when I played with those this kinds of model with it's just whenever you do a trend estimation, you typically assume a random walk. So to give you a very simple example, you know, the UTLR would be a random walk with some innovation mu t. The estimate can be very sensitive to the hyperprior controlling the variance of that object. And when I play with it, I could get a lot of different results. I'm not saying this is the case here, but just in general, whenever this is a tricky, difficult issue. Okay, so the last question one might ask is what should we target as unemployment? Okay, what is the optimal level of unemployment? And again, this is a different question, and therefore you have a different concept. Now, I'll just say as a side comment that, you know, if you look at Barrow Garden, this is not necessarily a policymaker's target. Maybe the policymakers want to go below the efficient level or the natural level. That's a different thing. Okay, here's more like Congress thinking, okay, what should be the level of employment that the Fed should target, say. Okay, and so the idea of the Michel SS paper is just, okay, if you have search friction, there's a search externality, and unemployment may be too high or too low. And how do they find the optimal unemployment? Well, the idea, you minimize unemployment, but you have search friction. So there's a hiring cost here and it's convex. Okay, so that's going to give you a nice problem where you can find some optimal level of unemployment. So I have Pascal's very nice pictures. I just put it back. Okay, but basically you have this technology constraint, which is the Beverage Curve. And as you lower unemployment, you need a lot more vacancies. It's convex. You need more and more vacancies to keep bringing down unemployment because of this search friction. So that's this Beverage Curve. That's the technology constraint. And then you have this welfare function. So this iso-loss curve, or iso-welfare curve. And at the optimal, the two things should be tangent. So the way I see this optimality condition, I mean, it's not a specialist here at all, but that's how we understood it. So it's just you have this kind of relationship. Marginal rate of transformation is equal to marginal rate of substitution. So the slope of the Beverage Curve is this technology constraint on hiring, and it's the slope of that, if you want, that matching function, if you want. So you have the Beverage Curve, there's this matching function in the background that for any unit of V gives you some more U, okay? And how much V you need to put to create one more U, that's the technology. And at the optimal, it should be equal to the society's marginal rate of substitution between U and V. And what is the marginal rate of substitution between U and V? What is the society's marginal rate of substitution between the two? Well, it's the marginal cost of employment over the marginal cost of vacancy. So what is the marginal cost of unemployment? What is the difference between the marginal utility of working and not working? Yeah, that's this object, and the marginal cost of a vacancy was the marginal utility here. And so if you rewrite those two objects by dividing the marginal value of working, marginal utility of working, you get that relationship, which Pascal and Emmanuel's relationship, that you have the ratio of these two marginal rate of substitution. Okay, and they call them zeta and kappa. So kappa is the marginal rate of substitution between vacancy and employment. So how many vacancies you need to put to create one more unit of employment? That's the hiring cost. And then the marginal rate of substitution, that society's cost of having an unemployed versus an employed person. And with those three elasticities, so epsilon, the elasticity of some matching function, zeta and kappa, these are the sufficient statistics you need to get the theta star, and theta is the vacancy and employment ratio, and that's what they try to measure. So I really like this. I just have comments that about the zeta, kappa, and epsilon. So the question I had is, are those guys constant? I understand that this may not be very sensitive at the end of the day to this concept because Pascal showed some ranges. But if I look at the epsilon, so elasticity of the Beverage curve, right? The log, the elasticity, so the slope of the log slope. So going back to this identity, S over S plus F, and if I use a matching function, so that we've seen from Lalande before, and I put them together and I linearize, log linearize, I get this relationship, right? And I get d log u equals d log v times this factor, and that's the elasticity that Pascal has been showing. And there's this other terms, that the change in the inflow rate, the separation rate, and the change in the matching efficiency. So those two last terms are ignored by Pascal. And you just look at that reduced form relationship. Now, one thing I'll say is that in the data, S and mu may co-move actually with V, or V over U. And therefore, what you estimate in the data may actually already subsum those two guys moving. So that the theoretical Beverage curve may not be the same as the empirical reduced form relationship that you estimate when you regress V on U, or F on theta. But that being said, that the paper by Ann and Crane addresses exactly that problem. That what about S and mu t? How do you do this dynamic Beverage curve decomposition that takes into account separation rate and matching efficiency? That's precisely getting at this potential issue. Okay, and same thing here. That approximation is a steady state approximation, and the paper by Ann and Crane gets precise at this problem by allowing for deviation from that steady state approximation. Okay. So that constant elasticity, I'm completely fine with. I have no problem here. Same thing for the constant recruiting cost kappa. That's like exactly what you assume when you write down the standard Maudslin-Pissarris model. It's just saying that the cost of hiring per posted vacancy is constant. And then there's going to be the friction that's going to make the cost convex, but not the cost per posted vacancy. The last one I don't know. That's just me by ignorance. Is it okay to, or is it a problem to assume that the marginal rate of substitution between U and N is constant, that zeta term, right? So my thing is, what if there are important nonlinearities? So should it be constant, that guy? What if there are worker heterogeneity, right? So this difference, so this, say this, this advantage groups, there's advantage groups, and as you move the unemployment, right, you put you might put more weight on one group versus another if there are more of them in the. I don't know. I just, it was strange to me that they would not should come into play at some point. And the same thing, I mean, Pascal already finds it, and Pascal has already find that there's too much slack, but there might be other externalities than the search friction. You think about discrimination, unequal access to financing, information, education. There might be a lot of other externalities that actually suggest that it might be even more slack than compared to the efficient level, right? I mean, going back to that Okun's paper in '73, where he was just saying there was some benefits of running a high pressure economy because it compensates those externalities. So this discrimination, once firms have hired all the guys they typically hire, they might start going after the people they typically discriminate against. And so there's that benefit of running a high pressure economy. And would that show up in that zeta term? I don't know. I mean, it's I keep going around whether that zeta term should be constant, or if it wasn't constant, what it would behave like. Anyway, that's just the last question I had. But just to summarize, I had a lot of fun reading all these papers, and I think it's a very exciting topic. So thank you.
Thank you. Thanks a lot, Regis. So we've come to the end of the presentation and discussion. So now I'm going to ask anybody in the audience if you want to ask a question, feel free to do so. So you can do so, by raising your hand, and I allow you to talk, or by typing something in the chat. And so let's see if anybody wants to ask something, and if not, I'm going to ask the first question. Okay. All right. So as we wait, for reactions, and I wanted to ask a question. So first, thanks a lot, Regis, for doing this great overview discussion. I don't regret, having a general discussion, giving us the big picture like this. That's really, really informative. And that made me think, so, and I wanted to ask a question to the team, Hijo and Leland, about the second paper we saw. So you say S moves quite a bit, and therefore and you say also the beverage curve is much steeper, the structural beverage curve is much steeper, than the real one. But I wanted to understand clearly, the much steeper doesn't come from S moving around, it comes from your Cobb-Douglas coefficient being estimated, much bigger or much smaller, than ours. Is that correct? Or is it the S effect that drives all this?
Oh yeah, sure. I think I guess I would say that it was both. That if we use a different elasticity, then the kind of multiplier on that separations rate will be smaller, and you should end up with less of an effect. It'll dampen the effect of separations on the intercept. So I think if you use our kind of framework, that identity, then regardless, you will have separations shifting the intercept at least somewhat. But having the large alpha coefficient kind of amplifies their effect. If that makes sense. Yeah, so I think it's just a combination of the both. Just separations are moving over the business cycle in a smooth way that doesn't necessarily lead to a discrete shift in the beverage curve, but the larger elasticity also amplifies their effect.
Okay, thank you. Isigul, you wanted to ask a question, say something? Go ahead.
Yeah, so I have two questions. One is to Emmanuel and Pascal. So you have, Regis talked about them, you have these two kind of moving parameters. One is the value of non-work, the other is recruiting costs. They're both debated a lot about. So what I was wondering, whether you could say something about, assume what we observe is efficient and back them out one by one. What would you get? Because especially this value of non-work, it's highly convex. You put 0.96, you get 20%. What do you need to put to make unemployment efficient for these two, one at a time? So I think it would be a cool thing to say, because now we have better estimates of this. I think it's between 0.5 to 0.7, but I would still like to see like that number. It's probably very high. And the second question was to Hiju. So you are extracting information from duration distribution of unemployment. In the ideal world, flows imply a duration distribution. But in the data, they don't, because flows are not Markovian and there are inflows at high durations. So I was wondering which one of these is giving you this extra information over the flows.
Okay, so let's go maybe in order. Pascal, do you want to respond?
Yeah, sure. Yeah, that's a great question and suggestion. So actually, we do exactly that in the paper at the end. So first we estimate these statistics and we show what you get, and we show the robustness when you get a range of kind of plausible estimates. But then we do exactly what you suggest, and we say, assume that the world is efficient. What would that mean for different statistics? And so we get a time series. It's towards the end of the paper, we get a time series for the recruiting cost, and we get a time series for the social value of non-work. if the world was efficient. And so, for instance, for the social value of non-work, of course, what you get if you assume that the world is always efficient is that your social value of non-work is very counter-cyclical. So it's very close to 1 in bad times to justify the high unemployment rate that we see. And it's very low in good times to justify the low unemployment rate that we see. And so, if anybody who thinks that, okay, the world's always efficient, at least you can use our framework to back out a series for the social value of non-work that you can use to justify that always efficient assumption. So we have exactly, if you look at the paper at the end, we have exactly these graphs. And if I may add just in one second to answer Regis's question, because it's related to that. So on the cyclicality of the social value of non-work, actually there is work by Chodorow-Reich and Karabarbonis that shows that it looks like the value of non-work moves together with labor productivity, which over the cycle, which implies that our zeta statistics should be fairly stable over the cycle. That's one thing. And then the other question about whether there are kind of social benefits from low unemployment, there is a literature, that looks at the link between, say, unemployment and crime, for instance, with the idea that maybe lower unemployment reduces crime and that has benefits that we wouldn't capture because we use this revealed preference approach. But so here, if we have good evidence on this other positive or negative effects of unemployment at a social level, you could tack that onto our estimate and then plug it into the formula, and that's what you would want to use because we are really after a social value of non-work. It's something we discuss a bit in the paper.
Thank you, Pascal. Hiju?
I appreciate the great question about the non-Markovian nature of the labor force flows. So especially when we think about the unemployment hazards, the non-Markovian nature, in other words, it means the perhaps the history dependence of the the transition between one state to another is actually captures the duration dependence. And then in my model, the duration dependence is captured by this, the slope and curvature factor and vector loadings. And in all the components that determines the unemployment hazards, at each point in time, are, vary over time. So meaning that, in my model, the duration dependence perfectly varies over time. So what does it mean? So if there is a, large, increase in the, composition of workers who have, perhaps unobserved worker heterogeneity that makes their, job finding probability low, then that, or if there is greater unemployment scoring from the previous employers, or something like that, or a larger human capital depreciation, that all these factors are flexibly captured by the vector loadings and the vectors, because all these components are allowed to vary over time. So I would like to emphasize that these non-Markovian natures are captured by the the duration structure, the slope and curvature factor, and in my model, any time variation in this non-Markovian dynamics is captured by this time varying parameters. And also you mentioned that the hazard does not necessarily imply the distribution of unemployment duration, right? And another source is actually the measurement errors. It is widely known that there are some spurious transitions between long-term unemployment and non-participation in long-term unemployment. So, I mean, one caveat of my model is that, in my model, this spurious transition is not explicitly, considered, but, my model takes more signal from the reported duration, distribution of unemployment duration when it tried to estimate or identify the trend of unemployment. So I would like to mention that. Thank you.
Thank you. Let me see, does anybody else want to ask a question, either from the audience or from the panelists? Lennon, go ahead.
Thanks. Yeah, I just had a quick question for Isagul. For the mismatch statistics, which data sources were you updating those from? I know you'd used different data sources in the past. Is the JOLTS and CPS, or are you using any of the other vacancies data?
So when we use industry as the measure of skill, it's JOLTS and the CPS. When it's occupation, it's burning glass and the CPS.
Burning glass. Okay, thank you. Interesting.
Any other questions? I don't see any hand from the attendees. I hope you can raise your hand. Oh yes, there was one. Stephen Brown at CEA. Go ahead. Let me allow you to talk. Go ahead.
You know, in order to squeeze an optimal unemployment rate out of the Beverage Curve, you have to assume this ISO welfare function between unemployment and the vacancy rate. Now, could you say something about where that comes from and why you think that shape of that curve is stable over time? I mean, in particular, the problem with the Phillips curve is that it's basically stopped fitting in the last 20 years. Why do you think you can do any better with a Beverage Curve derivation of the NIRU? End of over and out.
Very good question. Pascal, do you want to answer?
Yeah, sure. So first, I mean, I think the Beverage Curve is just, it's much better to use than the Phillips curve for the reason that you said. The Beverage Curve is visible in many labor markets. It hasn't disappeared. It's quite a stable relationship over long periods of time, like decades or more. It does shift, but usually the shifts are very clear. So it seems to be something that's just much easier to use than the Phillips curve. So then the ISO welfare curve, the shape, you need very little assumption for our analysis to work. We just need to assume that at a social level, when you have more unemployment, it's less good. And also when you have more vacancies, it also comes with a cost. And this comes in any model of the labor market, you will get that, because when people are unemployed, they are less productive than when they are employed. And when people work on recruiting, they are not able to work on production. So actually, it really captures a very broad range of models, this type of framework. And you don't need anything more than that, just assuming that having unemployed people instead of employed people is costly, and having people doing recruiting instead of production is costly. These are the only assumptions. So then the last point, and that's a bit more subtle, is whether the shape of that curve is going to change over the business cycle. And this goes back to the question in the discussion about whether our statistics, the social value of non-work and the recruiting cost, are changing over the business cycle. If these two statistics are changing, this would mean that the slope, is changing. So what we have to figure out is whether these things are stable or not. For the time being, there is a little bit of evidence that these things are fairly stable, but there is very little work on that. And I think we just don't know that much because we don't have enough kind of high frequency data on that. And I think, if people, if that formula is useful, hopefully there'll be much more work to figure out whether recruiting costs move over time or not, and to figure out whether the social value of non-work moves over time or not. And it's not necessarily difficult to answer this question. So for instance, if JOLTS added a question in the survey asking firms, hey, how many man hours do you spend every month on recruiting, on top of asking how many vacancies do you have posted, then we would have a time series that tell us actually how the recruiting costs move over time. So it's, all these things are, I think, very doable in the future.
Pascal, as I have you, Nicola Petrovsky-Nadeau asks, have you derived the results under directed search?
I mean, directed search is just an assumption about how wages are set, and our analysis works, it works for any type of labor demand, any type of wage setting. So in particular, a model, with, like, say, a DNP model, like in the tradition of Moen, with directed search, our analysis applies, and the efficient unemployment rate in that model is the same as the one that we get here. The only issue is, of course, that these models predict that unemployment is always efficient, and that seems to be inconsistent with the empirical evidence that we that we uncover. But the analysis applies as a special case to also directed search models.
Okay, Mark Giannoni, do you want to say something on Phillips curve?
Yeah, just a very quick comment. I mean, there's often the statement that the Phillips curve doesn't fit anymore. I think one thing that it's a little bit besides the point of today's session, but one thing that comes out of our paper here is that once you include data on inflation expectations, and that has been documented in many other papers, including other work by Stefano and Richard. When you include data on inflation expectation, the Phillips curve that is not as much of a mystery anymore. I mean, fits pretty well as well. So I just wanted to put that in people's mind again.
Thank you, and I have to stop because we're going to be cut off, within a few seconds at 5:45 exactly. But thank you, everybody. Thanks to the presenters. Thanks especially to Regis, discussing from Europe very late for him. It was really great to have you. Thank you, everybody. Goodbye.
Thank you.
Thank you all.
Bye.